And I'm doing this Chem 1 review stuff because it's been a long time since we've seen this. It didn't come up. This kind of stuff just did not come up throughout the year for the second half here, second class here, AP Chem. So let's make sure we remember how to do these things. I did Friday, I did basically the atomic structure, electron structure, that kind of stuff. Now I want to go over some of the problems you might see that are not that difficult, but if you've forgotten how to do them, they might be. All right. So, for example, for empirical formula, if it wants you to find an empirical formula, it gives you information like this, either grams or percentages. Either way, how would I find the empirical formula of this compound? What we normally do for finding an empirical formula, we look up the charge of Sn, we look up the charge of O, we put them together, we balance them out. But here I'm saying I've got a guy that I don't know his charges. A lot of times for empirical formulas, they're going to be carbon and hydrogen, where there's multiple ways you can put the guys together. All right, so how do you do that? If you don't remember, here's what you've got to find. First, you got to convert your given information to moles. And if you're given grams, it's easy enough. All right, and you don't have to show any of this. It's already done for you on the paper, obviously. I'm going to do one in a minute because it's got a little twist to it. So you're going to convert your stuff to moles, and then you're going to divide by the smaller number. Remember doing this? It's been a long time. I bet you've probably forgotten. And there's another twist at the very end of this that you have to know how to do as well. All right, but that will give you the ratio. See, once you got it in moles, you divide by the smaller number, and you can see that it's a 1-to-2 ratio, so the formula is SnO2. Okay? So let's try that with this guy, which you have room to do down here with me. All right? What am I going to do? Well, you say, I can't do this. I'm not giving grams. What happens if you're given percentages? What could you assume? What could you assume? How many grams can I assume that would make 4.58% a very easy number to convert to grams? 100. What's 4.58% of 100 grams? 4.58 grams. So that's all you got to do. That's the first little twist to this, is if it's given percentages, you just assume you have 100 grams. That's not a problem. All right? So you got 40.9 grams of carbon, and I'm going to convert him from grams to moles. 1 mole contains, and I need your calculators out. You want to do this one with me here, because there's a twist to this at the end as well. 40.9 grams, 12.011 grams is the atomic mass. I convert him to moles. Somebody do that for me. Caitlin, do that one while we set up the next one. 4.58 grams of hydrogen, grams at the bottom, moles at the top. 1 mole contains, for hydrogen, 1.0079. For 54.5 grams of oxygen, grams at the bottom, moles at the top. 1 mole contains 15.999. Some people, right now, let's stop you right here. Some people say, well, why am I not using the diatomic oxygen? Because it's not diatomic oxygen. It's not oxygen by itself. It's in a compound. So I'm not taking into account the fact that there's oxygen by itself is diatomic. I'm just going to use this periodic table molar mass, whatever atomic mass. Okay, what'd you get for that first one, Caitlin?
3.41.
3.41. What'd you get? Anybody get the second one yet? 4.54. And the last one, I believe, is also 3.41. Is that correct? Yeah. All right, now they're all in moles. Now watch this, okay? Because it's not going to happen the way you want it to. Last one I showed you as an example, it came out to be a nice 1-to-2 ratio. So your answer was SnO2. This guy, it's not so obvious what the ratio is, and when I do get it, it's still not going to be right. I'll have to do one more step. So what I have to do is divide by the smallest possible number I've got up here, 3.41. And what I get is 1 and 1 down here. But what do I get for this guy? 4.54 divided by 3.41 gives you what? 1.33 repeating or something like that, right? 1.3 something. All right, what do I do with that? That's the correct answer. Right now, that's all it is. It's C1, H1.3301. That is the empirical formula. The problem is it's not in whole numbers. What's the smallest whole number I can multiply this guy by to turn it into a whole number? 3. If I multiply him by 3, I will get 4. Do you see why? It'll actually be 3.999, but it'll be able to round it up. If you're within, a tenth, you could definitely round them up. But if I do that to him, I got to do that to him, and so my actual empirical formula is C3H4O3. Now I bet you would not have remembered how to do that if I didn't go over it, and that's why I'm going over this with you on the review day. Okay, so from Chem 1, Haven't seen that in a long time, but that's how you would do an empirical formula problem if you see one like that on the test, okay? All right, let's do another one that you haven't seen in a long time. And yes, we're going fast. And at this point, we're going to do some limiting reactant stuff. Limiting reactant, it's not like we haven't seen that at all. We just don't stress it a lot because most of the time you know what I'm given, okay? But it's the guy who's present in least abundance, the guy that you have the least amount of. And I use as an analogy here, making a hamburger, for example. If I have to make a hamburger, I can't make, just because I've got enough cheese to make 1, 2, 3, 4, 5, 6, 7 hamburgers doesn't mean I have enough to make 7 hamburgers. I only have 3 patties. That's going to be my limiting reactant, so I can't make any more. That's how it works in chemistry too, okay? So if we take a look at this guy, in this one it's relatively simple. Can you see who's in lesser abundance here for the first one? And I'll show you a little trick here, a little hint is right here. The way you can always tell is divide the moles you're given by its own coefficient, and whatever is a smaller number is going to be the guy who's the limiting reactant. So if I divide 1 by 1, I get 1. If I divide 4 by 2, I get 2, right? So the smaller one is this guy. Now what that really tells you is this. It doesn't just tell you that he's the limiting reactant. It also tells me I'm going to ignore him. There's going to be excess of him. I don't care. All right? I don't want to know. I don't use him to figure out these other 2 guys. I only use him. And then it follows the same way it always follows stoichiometry. 1 is to 1 as 1.0 is to 1.0, and there you go. That's how many moles of magnesium chloride you would get in this problem. How much hydrogen would I get? Same thing, 1.0 moles. All right? But if I did ask you how much of this was left over, what would you say? For every 1 mole of Mg, I would need 2 moles of HCl. So how much leftover HCl is there going to be in your container? I would have used up 2 moles, right? So there'd be 2 moles excess left over. What would I have to do in the case of these 2 guys? Again, I don't have time to do all these, but you could try these on your own if you want to practice. In these guys, can I just divide 24 by 1 and 36 by 2? No, I have to convert them to moles first and then decide who's the limiting reactant. Once you know that, then you can divide by your coefficients. Once you know in moles, divide by your coefficients and use only that guy. Use only that guy. Okay? So for this one down here, can you figure it out? It's a little bit uglier numbers. What do you think for that guy? And then we'll finish up this whole chart. 7 divided by 4 is what? Basically 1.75, right? And 6 divided by 3 is what? 2. So the smaller number is this guy, right? So that's the correct, that's what we're going to use. So we're going to use 7 moles. Now, here's the problem. I know he's a limiting reactant, so I'm going to use him. If I try to go from 4 is to 6 as 7 is to, it's kind of hard to do in my head. But can I do this in my head? This guy's going to be half the size, right? So what's half of 7? Now, this, by the way, what I'm doing here isn't just for fun. I already looked it up, I double-checked and triple-checked, and I'm always amazed by this. Although physics lets you use a calculator, you should know, and I've told this before, you will not get a calculator in the entire multiple choice section of the AP exam for chemistry. You just don't get one. So a lot of this stuff is going to be things like this, where you've got to do them in your head. They're not going to be ridiculously hard. You're not going to need to use a calculator, but you've got to use your head. For example, if I use my head and got 3.5 for this, I now maybe can see this one a little bit easier. This guy's 3 times as big as that, right? Can I figure him out? What's 3 times 3.5? 10.5, is that right? 10.5? All right, so that's how you would have to do that in your head. Okay, so there's a little bit of stoichiometry, limiting reactant kind of stuff, okay? Now, I am not going to, I know the next, oh yeah, I know the next thing in your paper, next 2 pages are on Vesper Theory and stuff like that. I did that because last year I had not covered this until this point. You guys have all those notes. I'm not going to go over them. I'm not going to give you those again. I am going to just talk about them for a few seconds at the end. But right now I want you to skip to the last page, which is blank, and we're going to do a percent composition problem on there. And okay, so percent composition. I chose this guy right here because it's a guy we actually saw in a lab we did for copper sulfate, and we had to do the percentage of copper in copper sulfate. Now, I could ask a lot of questions on this guy. Copy this one down real quick, and we'll just do this one example for a percent composition. I could ask this a lot of ways. What if I ask, it's unlikely on a test they're going to ask you to find a percent composition of the entire thing. Okay, what might they ask? Well, they might ask, like I asked in your lab, find a percentage of copper in copper sulfate pentahydrate. Okay? So what would you have to do? When you find a percent composition, it's always the same formula, part over the whole times 100. So you would have to know your mass of copper and then your mass of the whole thing, right? So let's find the mass of the whole thing first. Let's find the mass of copper sulfate pentahydrate, because that guy's a hydrate, so you got to know how to use that too. So I would say I'm going to take my, the number of atoms of each one of these guys for copper, sulfur, oxygen, H, and O, the number of atoms times their atomic mass to get the molar mass. That's your whole. That's your total, right? Number of atoms times the atomic mass, and then equals the molar mass. I've got 1 copper, 1 sulfur, 4 oxygens here. How many hydrogens? I want to throw a hydrate in here. How many hydrogens do I have? 10. And how many oxygens? 5. So I've got to do all of that, okay, and then add them all up. So really quick, 63.546, 32.066 grams, 15.999, 1.0079, and 15.999. You can finish that at your leisure. I don't want to waste any more time here, but we'll get eventually, when you add all those up, the molar mass. Now, let's say, again, you don't have to do that. Let's not get a calculator out. This is a review, so I'm not trying to get the exact perfect answer. Let's say I get that molar mass, whatever that number is. Say it's like 257.5. I don't know. Just making up a number. If it asked me for the percentage composition of copper, I would take this number here and divide it by that number and times by 100, right? That's how you get a percentage, correct? What if it wanted the percentage composition of water in the compound? We actually did that in one of our labs as well. I would take the mass of both of these guys, right? And I would divide that by the molar mass. But it's always by the whole. Always divided by the whole, depending on what it asks you to do. All right, and it doesn't have to be a hydrate. Say that was just a regular compound, CuSO4. Same thing. You would take the mass of this guy divided by the mass of the total, and that's what you'd do. Okay? So without wasting any more of our time, that's a percent composition route, which we have not done all year, just like we haven't done the empirical formula problems all year. Average atomic mass we have not done since probably September in Chem I. We're talking, for some of you, 2 years ago since we've done a problem like this. What is again? You have to the same thing on the back side. This is just, you have the second half of the back side. Copy this guy down really quickly as another review. This is the last one of the new problems, and I'm done. I'll talk to you a little bit about the Vesper theory and sigma and pi bonds, but I'm not going to actually give you the notes again, because this year I've already done that. Last year, when I got to this point, I had not covered all that stuff, and I had to actually teach it from day one. This time I'm just reviewing it with you. So just write that down quickly, and we will do one example of this. Next year I'll make sure I have this already on your packets, so I don't have to be writing this and wasting time. And I'll also get rid of that Vesper stuff, because we already had that. But I may keep part of it just for review. It's already filled in for you, because that is something that we covered very, very early in this year, so you may have forgotten it. You're going to get practice on it, though, over the course of those practice tests, I'm sure. All right, so if you look at a guy, if you didn't finish that, that's going to be gone away in a second. Look at this is what I'm saying for an average time mass. That number in the periodic table, the number that you see here in the bottom for the atomic mass is actually an average. For example, for lithium, there are 2 isotopes of lithium. If you average those 2 together, okay, carbon has 3. Fluorine, there's only 1 isotope, so that's what he is. All right, and so on. How do we get that average? Do we add them up and divide by 3? Absolutely not. It's a weighted average. That's what's different about this. You can't just add up the mass of this guy, that guy, and that guy, because here's what that would be like doing. Let's say you've got a 95% on a 10-point quiz, and you got a 98% on a 20-point quiz. But then you've got a 50% on the 100-point test. Okay? You got a 50 on the 100-point test. I can't just add up 50, 98, and 95 and get your average, can I? Your average is going to be much closer to that 50, isn't it? Right? Same logic applies here. So how do we do it? I know you haven't done it for 2 years or sometimes 3. Let's just do this one example. I'll show you how we do it because you probably forgot. And this is the last problem I'm going to do today. I will talk a little bit about sigma pi bonds and that stuff. I'm just going to go through it very quickly because you already have those notes. And then you're basically on your own. You're going to spend the next 2 weeks doing these problems, these packets, and these practice tests. And you will get out of it what you put into it. It's as simple as that. All right, so how do I get a weighted average? You know, in the days before, it's funny. Everything's done with computers now. But when I first started teaching, almost no teacher did their grades with computers. All right. So if you wanted to do like, I want to have my lab portion of the class worth 20%. I want to have my tests worth 40%. I want to have my homework worth 15%. Then you had to do this. This is exactly what you did. And very few people did. A lot of people just use a total points basis. But I do know people who did this. And there are still people who do that, only they set it up on the computer on a spreadsheet where it does this. So basically what I have to do is take 69% of that mass, 30% of that mass. Where's my answer going to be closer to, obviously? It's going to be closer to that guy. But the average is going to be not really an average when we think of it. It's a weighted average. So simply take 0.6917 times 62.939 AMUs, atomic mass units, and 0.3083 times 64.91 AMUs, 915 AMUs. And you will get those two numbers. This is not a lot of work, so just get those two numbers quickly, and I'll show you what we're going to do here, because this won't take very long. What did you get for the first one there? 43.53? 43.53. And that's the right number of significant figures. 4 significant figures here, 5 there. Only 4 should he have. How many here? 20 what? 20.01. Now, what's a nice part about this? And I hope you remember this. What should that add up to be?
100.
Not 100. That is what, oh, by the way, I didn't say this, but that's a good point. If I had done the percent composition of a guy like copper sulfate, and they actually wanted you to get every single element in there, what would they all have to add up to be? Yes, they'd have to add up to be 100. But in this case, they will add up to be that number up there for copper. And copper is 63.54. And that's what you should get. Now, you may not get exactly the number. It might be off by 100th or 1,000th. Because of rounding off and because of multiplying, you have to round off at some point because of significant figures. But it should be very, very close to the correct answer you get in the periodic table. Okay? So that's how we do those. Now, I don't believe there are any more like that. Right, okay. So now, I'm just really quickly, before, unfortunately, I have it only on my other computer, so I kind of have to take this apart and put it together here. Okay, take a look up here with the Vesper Theory and stuff like that. Now let's see if I can get this to work here real quick. I think I will. All right, cancel. No. This is not, well, that's okay. I'll just use this in here. All right, look at it, people. Shh. Vesper Theory. Remember this? Sigma and pi bonds? You probably don't. So just really quickly, let's go over this. All right. Sigma bonds are formed, and you don't have to write it. Don't try to write all this down. It's already in your notes, okay? Next year, if I do this as part of the review, I will summarize it and have it already in there so you don't have to try. I'm not going to waste 20 minutes or 25 minutes trying to write all this down. But I'm sure you've forgotten this because it's been so long. This is one of the oldest topics we did this year. Okay, sigma bonds are formed from basically single bonds. All right, allow overhead s orbitals, basically. And then pi bonds are formed from overlapping p or d orbitals. All right, these guys here, when you see the picture, you'll see how they're able to rotate. Double and triple bonds contain one sigma and one pi bond. I'll show you that in a second. Triples contain one sigma, two pi bonds. And single bonds in organic molecules usually have sp3 hybrids. All right, so what are we doing here? This is what happens in organics. It's not probably going to be a lot of this, but there could be a question about hybridization. And normally when I draw carbon, what does it look like? It looks like that. But that's not really what happens when carbon gets together. All right, it doesn't really have a 2s2 and then a 2p2. That's not very stable. This guy being one away from being half full. What happens is it kind of meshes all four of these guys together. sp2 and and basically what you get here are sp3 hybrids. All right, 3p orbitals, which look like this, one s orbital look like that, become 4 sp3 hybrids. These guys right here, all right, and form a tetrahedron all at equal angles, all the same. You know that from doing a little bit of organic chemistry, earlier in the year. Now, when these guys form bonds with other ones, if they have sp3 hybrids, you generally get single bonds. That's what you have. But they can hybridize in different ways. I could just put together, for example, one s orbital and 2 of the p orbitals, sp2 hybrids. That leaves one, this purple p here, open to be able to form another bond above and below it. All right, and that's why it looks, oops, strange. Not sure how that happened. Not sure why that. Here, take a look. So you have the sp2 hybrid, all right, would be forming a one bond here and the p bonds forming over there, so it doesn't allow rotation. Now, the big question is, can you tell? This little chart here is actually on this sheet, along with a lot of the other stuff. That's kind of a review sheet I made for you. You don't have it yet. I'm going to give it to you in a little bit. On the sheet, you have this little chart. And basically, if it asks you, if it draws a compound and it wants to know how many sigma bonds or how many pi bonds, you got to remember, if it's a single bond, all right, it's basically going to have only a sigma bond in it. If it's a double bond, it has both a sigma and a pi. And if it's a triple bond, it has a sigma and 2 pi bonds. The weakest bonds are going to be just the single bond. Triple bonds will be much stronger and therefore much shorter, closer together, pulling those atoms closer together. The weaker bond will be longer, okay? Free rotation about a single bond and no rotation about the double and triple bonds. We had all this. It may not all be coming back to you right now, but we did have it. And a lot of times the questions will ask you about sigma and pi bonds. When you're doing these papers back there, those practice tests, I want you to use, until like next week, I want you to use your notes. I want you to use review packets. I want you to use this sheet. Anything you want to find the answers. All right? next week, when we get the, I'll have you doing more of the AP Central exams. Then I'm going to have you try them on your own, like you did in physics when you had those practice exams, where I'll just kind of have, okay, you have this period to do them as if it was a test, so you have an idea of how to start pacing yourself time-wise and how much of this you've already gotten down. But this week is all about finding the stuff that you don't know and making sure you know it, so that next week when we take those practice tests, the other practice tests, the ones from AP Central, you will start to be able to do them without looking at this sheet, without looking it up in your notes. Okay, but it's okay to look it up. I want you to look it up in your notes right now. And that is it. I am done with the review. I'll talk to you. Let me just shut this off, and then I'll talk to you about what you're going to do for the rest of the